Okay, I think it's going. All right. Okay, good morning, everybody. Welcome again to virtual seminars for Precambrian geology. Today we have a talk by Dr. Lizzy Trower from the University of Colorado, Boulder. Talk titled Neoproterozoic Giant Ooids as Novel Proxies for Tonian and Cryogenian Seawater Chemistry. A really great picture of giant ooids that I'm sure she'll talk about. Next week, we'll have a talk from Cynthia Lee from Rice University. And the preliminary topic that I understand we'll be hearing about is definitely tectonics related, and hopefully about sort of the story of plate tectonics through time here. So with that, we're just going to have our normal scheduled presentation today with Lizzy's going to present for 40 to 15 minutes, and then we're going to transition to the question session. So I'll go ahead and introduce Dr. Lizzy Trower for us. So Dr. Lizzy Trower is a chemical sedimentologist, particularly interested in how and why chemical sediments form, lithify, and record chemical, physical, and biological paleoenvironmental conditions. She received her bachelor's degree from Caltech in 2009. She got started on working on Neoproterozoic giant ooids early with Dr. John Gratzinger. She went on to Stanford for a PhD working with Dr. Donald Lowe, investigating sedimentary silica in the Archean. She graduated in 2014. After her PhD, Lizzy did her postdoctoral research at Caltech with Woody Fisher. And she has now held her assistant professorship at the University of Colorado Boulder since 2018. She spent her career working on ooids and stromatolites and carbonate sediments, silica-rich sediments and sedimentary silica cycle, and applying carbon and silicon isotopes studies in the sedimentary record. Something else I was excited to see was that she has a patent for microabrasive compositions containing ooids, which I really don't know much about, but I'm just naturally curious now that I know that it exists. So on that note, Lizzy, please go right ahead and present for us. Thank you.
All right, thanks, Alex, for that introduction. If anyone wants to hear more about my patent for the use of ooids as microbeads, I'd be happy to answer a few questions about that afterwards. But thanks everyone for being here today. And thank you to Alex and Andre for the invitation. I'm excited to talk to you about some ongoing work that I've been doing, trying to figure out why exactly a bunch of ooids in Neoproterozoic time, and specifically in the Tonian and Cryogenian underlying snowball earth glacial rocks, are so large. But before I jump into it, I just wanted to acknowledge that all this work has really been a team effort. As Alex mentioned, I actually got my start getting really interested in giant ooids as an undergrad. And so I owe a lot of my early inspiration both to a really awesome paper written by Don Sumner in 1993, and also to my undergraduate research mentor, John Gratzinger. And then the rest of the work I'm going to talk to you about today, there will be a section on theory, experiments, and work in modern environments. And for that work, I had the support of my two postdoc co-mentors, Woody Fisher and Mike Lamb at Caltech, and also the support of Maya Gomes, who's my co-PI in work that we've been doing in the modern Turks and Caicos, looking at ooids there. All the other folks on the various ambergris Turks and Caicos field teams over the years, and also in Great Salt Lake. I'm going to show you some applications of my work on ooids in the Phanerozoic to give a little motivation that for why we think this approach actually works. And that's going to be highlighting a lot of work that was led by Xiaowei Li and Artie Koshiada-Tula, who are respectively were a grad student and a postdoc in John Payne's group at Stanford. And then finally, my recent reinvigoration of my interest in Neoproterozoic giant ooids, which basically started when I started as a faculty member here at CU, really owes its inspiration to my colleague, Carl Simpson, and then the work of a number of students here, including Ginny Walla, Sarah Jameson Todd, and currently Jim Gutowski. So if you showed up to this talk not knowing what an ooid is, I'm going to talk about it for the next 50 minutes. So I figured I should at least define what I'm talking about. An ooid is a type of concentrically coated carbonate sand grain. So this is a thin section, so a cross section of one of these grains from the sand from the modern Great Salt Lake. You can see that it has this nucleus in the center that's surrounded by this layered aragonitic cortex. In this case, the nucleus is a fecal pellet of a brine shrimp, but in different types of environments, these grains can form around whatever kind of suitably small nuclei exist in the environment. I think these grains are really cool, and I've been really interested in them since I first learned about them as an undergrad. I think they're pretty charismatic, and when you walk on a modern beach made of ooids, it's kind of awesome to pick up all this sand that's just incredibly spherical and shiny. But beyond just kind of the charismatic aspect of them, ooids are really interesting because they're really common in marine and lacustrine shallow water carbonate successions of all ages. So some of my inspiration has been the idea that there's a lot of unrealized potential in being able to use better, more mechanistic understanding of how these grains form to leverage them as proxies in deep time. And so I'm starting here with an observation that I first became aware of and that inspired my one of my first real research projects as an undergraduate, which is that although anywhere you can go today and find ooids forming now, and in the vast majority of cases in the rock record, ooids are sand-sized grains. That's how I defined them. But there are a few times in Earth history when these grains get much larger, more like marbles than sand size. And so this is actually a field picture I took when I was out doing some work for my undergraduate thesis on a set of Ediacaran giant ooids in the Death Valley area and the Johnny Formation. I actually was on this field trip when I think Kristen Bergman was out with me doing some of the first field work for her thesis back in the day. And so this observation didn't start with me. There is a really uneven distribution of these especially large ooids. So in this really simple histogram here, I'm just showing an example of the number of occurrences of ooids that are larger than 2 millimeters in diameter, which is a threshold that's traditionally used to call them giant ooids instead of regular ooids. It's been pointed out, or it's been suggested to me before, that this threshold is or it's been asked why the threshold is 2 millimeters. And as a sedimentologist, the 2 millimeter cutoff is actually the upper size limit of a sand grain. So it's not just a, well, that's where the cutoff comes from. But as you can see, the distribution of these particularly large ooids is not evenly distributed in Earth history. Many of them fall in the Neoproterozoic era, and as I'll get to a little bit later in my talk, they actually have an even more close stratigraphic relationship with snowball Earth rocks than just kind of generally existing in the same geological era. And so canonically, the idea has been that this uneven distribution of particularly large ooids reflects something about the carbonate mineral saturation state of seawater chemistry, that generally larger ooids reflect seawater that's much more supersaturated with respect to calcium carbonate than at other times during Earth history. And in this talk today, I'm going to talk about work I've done to test and apply the hypothesis that rather than this just being kind of a general relationship, but there's a specific relationship between ooid size and carbonate saturation state, which reflects that ooid size is this equilibrium trait reflecting a balance between precipitation and abrasion rates. And that means that it can potentially be used as a proxy for ancient seawater carbonate chemistry. Okay, so a brief outline of what I'm going to cover today, which kind of reflects a little bit of my journey in trying to better understand what drives ooid size. I'm going to start by telling you about work I started conducting primarily as a postdoc. So I'll tell you a little bit about the underlying theory of ooid size as this equilibrium trait. I'll show you the results of some flume experiments to actually measure some of these rates in the lab and applications to modern field sites. Then I'm going to show you some brief examples from the early Triassic and also the beginning of a Phanerozoic wide marine ooid size record that my colleagues and I have been working on to motivate a little bit that the ooid size tends to behave as one might expect in deeper time based on this understanding that I've developed from theory experiments in modern field sites. And then finally, I will get to this case of these Tonian and Cryogenian ooids that have really been this big, interesting question to me since really the beginning of my career as a scientist. So I know this is the virtual seminar in Precambrian geology, and I'm going to spend a big chunk of my talk not specifically talking about the Precambrian, but as a process sedimentologist, it's been really useful and important for me to be able to approach this question from the perspective of experiments and working in modern field sites to really get a good handle for how these processes are at play in places where you can see them in action. Okay, so I'm going to start with an observation, which is that this is about modern ooids. Modern ooids are old and they grow pretty slowly. So this cartoon here is meant to be a cross section of a modern ooid. This one happens to be from Ambergris Key in the Turks and Caicos, which is somewhere I have also worked. And it's showing the results of a sequential extraction radiocarbon analysis showing the ages of different layers of those ooids. You can see the outside layer is effectively modern, inside layer is 400 years before present, and the very inside, the first layer next to the nucleus is 1,000 years old. So, and this data suggests that the ooids in this environment have been accumulating for at least the past 1,000 years. And so there are a couple different sets of these sequential dating studies, and we can use those to estimate net growth rates of ooids in different modern environments. And I'm showing this data here. It's on the order of 1 cubic micron per ooid per hour. I realize that's kind of a weird unit, but to give you some perspective in that, if you took the measured carbonate saturation states in those environments and you just plugged them into our empirical precipitation rate relationships for aragonite under those conditions, considering a variety of different approaches to that, either including measurements of precipitation rates in the field. In theory, ooids in these environments from which these radiocarbon data come from should be able to grow at a rate that's about 4 orders of magnitude faster than these radiocarbon net growth rates. So that's a pretty big difference for the geological process. And I think it's interesting to start here and dig into why that occurs. So one way to think about this is that this is effectively perhaps evidence of something like the Sadler effect, but within individual ooids, right? If we were observing carbonate precipitation rate instantaneously, it could be really fast, but when we average the rate over the entire 1,000+ year lifetime of the ooid, it's much slower. And I think what's interesting in observing something like a Sadler effect in this case, in this situation, is to ask, what's driving these effectively hiatuses in ooid growth? And so I'm going to argue to you today that these hiatuses aren't just a lack of precipitation, they're actually because ooids are moving around often, frequently in their environments, and they're abrading with each other. They're sedimentary grains. They are found in energetic environments like tidal channels, shoals, etc. So this is an underwater video of ooids moving around on a shoal in the Turks and Caicos Islands. And so I'm also certainly not the first person to theorize that abrasion plays a really the size of these grains, and this dates back at least to Bathurst in the 70s. And so I'm showing here kind of a schematic representation of how he presented his idea about the relationship between precipitation and abrasion and controlling ooid size. So this yellow curve here shows a representation of precipitation rate, which precipitation occurs on the grain surface, so it would be a function of the surface area or the radius squared, and abrasion rate, which is a function of the grain's kinetic energy. So you might expect it to be related to the grain's volume, the radius cubed, which means these two rate laws have different curvature, and there's some grain size at which those rates are equal. So Bathurst's idea was that the point at which these two rates were equal represented a fundamental limit on ooid size. And so the idea, there's an implicit assumption here, which is that the rates are slow relative to ooid lifetimes, meaning that this is grain size on the x-axis, and ooid might spend its entire lifetime approaching this fundamental limit along this path. So this basically growth is monotonic. But given that I've just showed through this radiocarbon and other data that the potential growth rates for ooids in a lot of places where we find them now is really fast compared to their lifetimes, I think we might need to consider this relationship differently and think of this overlap point not as a limit, but more as an equilibrium. Another reason for that is because the environments ooids grow in, considering that they are growing for 1,000 or more years, are dynamic. They may not have the exact same aqueous geochemical or hydrodynamic conditions throughout those 1,000+ years, which means that the goalpost, so the point at which the two rates are equal, is not necessarily going to be the same throughout the entire history of a grain. So kind of the point at which it's reaching, at which those rates are equal, is going to be different. And so a key prediction of this idea is that you might expect that ooids are approaching this equilibrium from both sides, that some may overshoot the equilibrium, or the equilibrium point may change to a smaller size, and that you should see a range of ooids centered around a particular equilibrium size. It's dynamic. So another key aspect of this that's important to tackle is that abrasion rate is more complicated than just a function of the grain's volume. And this has to do a little bit with how sediment actually moves in an environment. So to kind of bring you back to something you may remember from sedimentology class, there's different modes that sediment can be transported in. One of these is bed load. So that's when grains are rolling or sliding or saltating, hopping along the bed. And in that case, they're having frequent but relatively low energy impacts with the bed. In other conditions, sediment can be transported in suspension, which means they're being carried by turbulence in the flow for these longer hops between impacts with the bed. So their impacts themselves are going to be less frequent, but they're going to be higher energy. So you can imagine there's going to be some sort of trade-off in terms of the actual kinetic energy and abrasion associated with these impacts, depending on both their frequency and the energy or the velocity of these impacts. So similarly, if you imagine some system that has, some fixed current energy, and you have grains of different sizes, these are all going to have different types of frequency and energy of impacts with the bed. So there may be some grains that are under these conditions that are so large that they're below the threshold of motion. They're not moving at all, and so therefore they're not abrading at all if you ignore any impacts from smaller grains hitting them. But these grains themselves are not having any impacts with the bed. Some smaller grain size will be moving in the bed load and saltating along the bed. Another grain size will be traveling in suspension and having those less frequent but higher energy impacts. And some even smaller grain size will be traveling in the wash load, meaning it effectively is almost never interacting with the bed. And also the grains are so small that their impacts will almost all be viscously damped, like they can't hit the bed hard enough to abrade themselves. And so what this means is that abrasion rate doesn't just depend on grain size, so the volume and kinetic energy of the grains, but it also effectively depends on the current energy. You'll see me refer to this in different parts of the talk as the bed shear velocity. But it basically, like, it matters how the sediment is being transported, whether it's in the bed load, the suspended load, et cetera. And so a really interesting aspect of this is a little bit of a schematic, but this is a abrasion model for sand grains, showing you generalized an idea of increasing current energy on the x-axis and abrasion rate on the y-axis. And so you can see some of these trade-offs here that actually the position of this peak depends a little bit on grain size. So this is for a particular grain size, but there's a peak in abrasion close to the threshold of suspension, which is interesting because that's actually the mode that a lot of ooids are transported in modern environments. And it drops off really quickly as you have less and less frequent impacts in bed load. Actually drops off also as you transport more grains in suspension, and that's because they're hitting the bed less frequently, even though some of the impacts they do have tend to be at higher energy. So now I'm going to kind of step back into a little bit of the framework that I was showing you with respect to the kind of abrasion versus precipitation model that Bathurst first came up with. So we're looking at a relationship of grain size on the x-axis and change in ooid volume, dV dt, on the y-axis. So this dashed line here would be an R cubed curve, an abrasion rate that depends only on volume. And this solid curve is an abrasion rate model that also depends on the bed shear velocity. So it cares how those grains, the transport mode that those grains are moving in. And you can see there are some important differences between these two relationships. So then we can add a precipitation rate, which I'm still going to have as a function of the grain's surface area. And you can see that there are a couple different domains between these relationships. That grains change in size should be the difference in these two rates. So for grains that are in this area where the purple line, the abrasion rate is much more rapid, this is a log scale than the precipitation rate, those grains should experience pretty rapid net abrasion, and vice versa in this side where the precipitation rate is much faster than the abrasion rate, those grains should experience net precipitation. And then there's a region over here where if grains are not moving and yet they exist in a carbonate supersaturated environment, they're going to tend to get cemented together into a hard ground. So it's not really an ideal environment for ooids to actually form if they're never moving. And you can see here, this green line is this point at which the two rates are equal. And you can see that at least in this model, there we have paths where grains can approach this equilibrium from both directions. And I just want to emphasize again that it's important to keep in mind that this equilibrium can be dynamic. If the carbonate saturation state of the environment changes, the yellow line, the precipitation line will change, which will change the point at which these overlap, or if the hydrodynamics of the environment change, so the grains are moving more or less frequently or in a slightly different transport mode, the position of the purple line will change. So what I'm going to show you next is some work that I did in Mike Lamb's lab, experimental geomorphology lab at Caltech, to try to actually calibrate some of these rates with experimental data, because although we have a pretty good understanding of carbonate precipitation rates, before this work we did not have a good understanding of like the exactly the magnitude of abrasion rates for sand-sized grains. There had been some work done on like more pebble-sized grains, but less on sand. So this is a schematic of the experimental setup I used. These are, they're called abrasion mills, but they're kind of like these small cylindrical flumes. They're filled with artificial seawater. There's a base here with a bunch of sand epoxied onto a disc. So that's basically the bed that the grains are hopping and abrading along. And I ran experiments using an artificial seawater mix that's moderately, but not super highly super saturated with respect to aragonite. And I used a couple different types of modern ooids as the starting material. So ooids from the Bahamas. You'll notice these are actually ooids you can buy as aquarium sand on the internet, and they are not the most beautiful ooids I've ever seen. They don't have a ton of layers on them, but they have, they don't have super thick cortices. And then these are lacustrine ooids from the Great Salt Lake. And so what's really cool is that you only need to put these ooids in these flumes for a pretty short amount of time. And if you take them out and rinse them off and look at them in the SEM, you can see a big difference in what the grain surfaces look like. So here the grain surfaces are a little bit rough. And here in these right panels are SEM images of grains after abrasion, and hopefully you can tell that the surfaces look much smoother. What's also cool is you can see these like networks of kind of curvilinear indentations in the surface, and those are actually networks of cyanobacterial microborings that are inside the ooid cortex, and so those have actually been revealed at the surface due to this like slow and even polishing process of abrasion. And similarly, in some of these experiments, I observed a different type of change in the surface texture. So again, here's a before picture and here's an after picture. There's this kind of interesting, like kind of crystalline new texture that's formed. In fact, in this case, I used cam sizer analysis to basically compare the sizes of grain populations before and after these experiments. And so in these trials where I saw this different surface fabric, these also corresponded to increases in the average size in these conditions. So I'm going to skip a few steps here and show you the outcome in terms of rates. So this is the same, these two panels on the left are the same that I showed a couple minutes ago. The net growth rates, which are pretty slow, some different types of estimates of how fast precipitation rate could be in ooid forming environments. And then here in pink are the estimated rates based on changes in grain size from experiments where the ooids grew. And in green are the abrasion rates from experiments where the ooids got smaller. And so something you can see is that these two sets of rates are similar order of magnitude to some of these estimates I come up with from these different types of sources. And so this is pretty interesting, and this is kind of effectively what we predicted, that this very small net rate can effectively be the result of the subtraction of two larger numbers. The difference between them is a smaller number. Another really cool result of this, that to visualize this in a different way, is that in these experiments, we actually saw ooids appearing to be approaching an equilibrium size in our experimental system from both directions. So now the y-axis on this plot is not a log scale. So these are positive values. These ooids grew that are above this dashed line, and these ooids got smaller that are below the dashed line. So you can see that, you can imagine that in the conditions in the system, there's some equilibrium size in the middle that grains were approaching from either direction, and it depended on their starting grain size relative to that equilibrium size. So before I jump into applying this to natural environments, I wanted to mention that there's a really important difference between the setup and particularly the sediment transport in these experiments relative to the modern environment. And that is that in my flume experiments, the grains are moving and therefore braiding pretty much constantly. There's not enough sediment in those experiments for them to really form bed forms. So that's not like the environment where most often, at least in modern environments, and you can convince yourself of this in the rock record by seeing bed forms like ripples or dune cross stratification, that in natural environments, these sedimentary grains are often at rest when they're inside a bed form, so inside a dune form. And the types of bed forms that they might exist in also depend on grain size. So for particularly large ooids, those would basically never be able to exist in ripples. They could only exist in dunes, whereas sand-sized ooids could exist in both ripples and dunes. So to apply this model to deep time, what we had to do was to include an intermittency factor, which you'll see me refer to as F a couple times later in this talk, to reflect that what matters is the grain's time averaged abrasion rate. So it's going to experience some actual abrasion while it's in motion, not stuck within a bed form, and then it's going to spend some time inside that bed form abrading not at all. So we need some rate to kind of reduce the time averaged abrasion rate to reflect the fact that it's not abrading all the time. So this would be a very simple relationship of what this equilibrium size hypothesis is, which is that at the equilibrium size in natural environments, the precipitation rate is equal to the abrasion rate multiplied by this intermittency factor to effectively reduce that abrasion rate to reflect that it's being balanced out by all these times of non-abrasion. Okay, so I want to take a second to kind of walk through a little bit of like the important parameters of this model before I show you some examples of trying to apply it. But what's exciting, I think, is that if this is true, that at this equilibrium size, precipitation rate is directly related to abrasion rate, it means that we can determine the seawater chemistry that can explain the size of different ooids in deep time, including giant ooids. And the reason this works is that abrasion rate is primarily a function of parameters that we can do a pretty good job of measuring or estimating based on observations from rocks. Grain size is actually the most important of these. Particle and fluid density are important too, but we know the densities of carbonate minerals like calcite and aragonite, and we have good estimates of seawater density, and we also know how to correct that for changes in seawater density and viscosity at different temperatures and salinities. Knowing the transport mode matters, but it helps that the bed forms and environments that these exist in suggest that most ooids are transported near the threshold of suspension, which allows us to use a non-dimensional term called the Rouse number to get a pretty good idea of what shear velocities those grains would be transported at. And then this transport intermittency term is really important because it basically modulates this relationship between precipitation and abrasion rate. In theory, that's going to be related to bed form size, type, and migration rate. And that's honestly the hardest one to constrain, and we would benefit from more work understanding like the dynamics of different types of dune forms in carbonate environments. So then precipitation rate is primarily a function of calcium carbonate mineral saturation state, which you'll see me show as this omega sign throughout the rest of the talk. But it also depends on mineralogy because basically the precipitation rate laws of calcite and aragonite are slightly different as a function of carbonate saturation state. And also importantly on temperature. So for example, both calcite and aragonite precipitate more rapidly as a function of a given an important thing to point out about this model framework is that it actually assumes that there's no intermittency with respect to precipitation rate. So there's been some of the classical models of ooid growth suggest that like all of the growth occurs while the grains are in suspension. And both in terms of its theory and mathematically, that's not how this model works. It's basically assuming that precipitation can occur at any time during the ooid's lifetime. And we're basically looking at kind of a time averaged precipitation rate and therefore abrasion rate. So including precipitation that can happen both within bed forms and when grains are in motion. So what that means, because we can do a pretty good job of constraining all these aspects of abrasion rate, and we can make good inferences on primary mineralogy, and we have other proxies that can help us get at temperature, so that we can effectively use measurements of grain size, D, with a handful of other observations to solve for omega. That's really potentially really valuable as a proxy in deep time, because if we can combine it with one other parameter of the carbonate system and some information about the, for example, magnesium calcium ratio in ancient seawater, we can also gain some inferences about other seawater carbonate chemistry parameters that a lot of us care about, like the total amount of dissolved inorganic carbon, alkalinity, PCO2, pH, etc. And so this little graph kind of shows schematically how the application of this would work. Okay, so these are bed shear velocities on the x-axis, and these black lines here show the Rouse numbers for thresholds between different modes of sediment transport. So most ooids exist in environments that are relatively close to the solid black line, which is the threshold of suspension. So for example, you could measure an ooid grain size in the environment, say 600 microns, follow this over to this relationship, assuming you have reason to suspect that these ooids are also being transported near the threshold of suspension. And you could use that to solve for the omega value. In this case, it would be somewhere between 4 and 6. Okay, so I've kind of showed you some of these rates and that we can see ooids approaching a theoretical equilibrium size in a lab environment, but even modern field sites are much more complex than these really simple flume settings. So the first step is to do a set of field tests to go to modern environments where we can measure all these parameters and basically predict what we think the equilibrium ooid size should be in that environment, and then measure the actual ooid sizes and see if we get the right answer. So this first example I'm going to show you is from Little Ambergris Key in the Turks and Caicos Islands. This is where the Turks and Caicos are located. Little Ambergris Key is an uninhabited island next to Big Ambergris Key, which has some fancy vacation homes on it. And one of the really striking things about this island that you can actually see in these more zoomed out satellite images is this 20-kilometer long ooid shoal. And actually almost all of this sediment surrounding Little Ambergris Key is almost all ooid. So this is a really cool modern ooid factory. The reason the shoal has this morphology is because the Turks and Caicos sit directly in the trade winds. So these little windrows diagrams are showing you wind data from both the non-hurricane and the hurricane season. And what you should take away from this is that in this environment, it's windy every day. It's basically like the typical wind speed is like 10 meters per second, and it's always coming from the right direction, and it's always windy. And so this sets up a series of wave fronts that move in the same direction across the platform pretty much all year round. And you can actually see this from bed forms, these wave fronts driven by this continuous wind refract around Big and Little Ambergris Key, and they meet in the middle and basically keep ooids on the active shoal. This is a series of satellite images, and if you try to pick out one particular bed form, you can follow it moving slowly to the west. So this whole shoal is basically like a westward conveyor belt of ooids. This is what it looks like standing on the shoal. So you can see some of these waves crashing in from either side. This is the view to the west here. These dark splotches here are some sharks. They're nurse sharks, but still sharks for scale. And again, this is this underwater video, a little bit bigger now, of what transport looks like on the shoal. You can see that grains even these grains on the bed surface are sitting on the bed for a while, but then waves come through and they're at least temporarily transported in suspension. I did a lot of other work in this site that I'm not going to have time to talk to you about today. In particular, one of the things we were interested in here was trying to see if we could assess the relative influence of microbes versus just strictly physical chemical processes on ooid growth in this environment. So I have a bunch of different types of samples from both along this shoal and all around the rest of the part of this island. But for the purposes of this talk, I'm just going to show you this data. So this is basically application of this equilibrium ooid size model to this setting. So we basically constrained the intermittency using dimensions and the migration rate of bed forms. We actually measured or calculated the aragonite saturation state by measuring pH, DIC, alkalinity, and major cation and anion concentrations from the seawater. We were able to do a good job of estimating bed shear velocity based on observing the modes of transport. And so this is the results of this model. These different lines are showing you predictions of equilibrium ooid size as a function of bed shear velocity for different values of intermittency. And you can see there's some range here, but in general, it's from about 475 to 650 microns. And in fact, that's almost exactly a fit for the range of ooid sizes we see in this environment, from about 450 to a little bit over 600 microns. Something interesting about this setting that I talk a lot more about in this paper is that there's a trend of increasing ooid size along the transport path of the shoal. And I think a reasonable explanation for this is that there's a change in transport frequency moving along the shoal, which is probably a relationship of the water depth increasing a little bit, which affects the migration rate of the bed forms. Okay, so I realize that was super fast, but basically the short answer is that in general, in this modern environment, in a marine setting and modern carbonate platform, the dynamic equilibrium model gets the right answer, which is really comforting. But something else I wanted to do was test it in a really different environment. So this is a photo now of Great Salt Lake. I picked this image for today because this is actually from this fall. The lake level has been at a historical low for a lot of 2021. And so a lot of these microbialite mounds are exposed. And if you take out my graduate student from this frame, I feel like it really looked a lot like the Precambrian out there. But beyond these microbialite mounds, there's also a lot of modern ooid sand along a lot of the shores of Great Salt Lake. And this in particular is a really interesting and I think valuable test of the equilibrium size model because Great Salt Lake is really different, both chemically and hydrodynamically, than a modern carbonate platform. So it's kind of testing like whether the same relationship works across a really broad range of these important variables. And to make a really long story short, I have a lot more information about this, including a cool project I did looking at the shapes of ooids in these different environments from Great Salt Lake. We also effectively get the right answer there, even though transport is much less frequent and the water is much less supersaturated with respect to calcium carbonate in Great Salt Lake relative to the Turks and Caicos. Okay. So finally, now I'm ready to show you some examples of applying this proxy to deep time, now that I've shown that it does a pretty good job performing in modern environments. And first, I'm going to briefly stop off in the early Triassic and highlight some work that Xiaowei Li did. So there are giant ooids from a couple locations in early Triassic strata, and he focused particularly on the ones in South China and using this dynamic equilibrium model to try to reconstruct carbonate chemistry from when those were forming. These histograms show the ooid sizes he measured from fin sections, and you can see that the median sizes are in the range of 2 to 4 millimeters, but some of these ooids are much larger, up to about like 8 or 9 millimeters in diameter. And one of the interesting things Xiaowei found when he just plugged this in or used this model framework to reconstruct these ooid sizes is that, so now you're looking at, these are different transport intermittencies and the predicted carbonate saturation state needed to sustain these different ooid sizes as the equilibrium size, that a vast majority of these ooid sizes that are common in these environments, including those 3 and 4 micron sizes, fall at carbonate saturation states that are way above 20. And so these are generally thought to be probably implausible to sustain over the 1,000+ years needed for ooids to form, because they're beyond the threshold for homogeneous nucleation of aragonite in the water column. So basically aragonite should just be crashing out of a solution with omega values this high. But an interesting thing about this model is that Xiaowei assumed a seawater temperature of 25 C, which is what we use for some of these modern environments. And it was actually warmer than that during the early Triassic. So instead, when he used kinetic data for 37C, which is consistent with a lot of other proxy data, this really helps resolve this problem that basically it was important for the formation of these large ooids in the early Triassic that it was both warm and that the ooids were composed of aragonite rather than calcite, because aragonite has a somewhat faster precipitation rate, allowing a larger ooid size to be the equilibrium size. We've also been doing some work, this is led by Artie, starting to compile a trend of ooid size data spanning the Phanerozoic. And this is a really broad brush effect because, as you imagine, there are probably a lot of regional differences, even in a particular time bin in carbonate saturation state, but some interesting things jump out here, such as that There's large ooids in the Cambrian, which also coincides in theory with aragonite seas and relatively warm conditions. So more evidence to suggest that the mineralogy and the temperature, which both modulate carbonate precipitation kinetics, are both important controls on ooid size, or flipped around, that ooid size is sensitive to the magnesium calcium ratio of seawater and also temperature. I'm not going to spend too much time on this because this is work on progress, but we've been using ARDI's data combined with other estimates of seawater ion concentration and PCO2 records to take those ooid sizes, translate them into estimated carbonate saturation states, and use them to make some estimates of these other aspects of seawater carbonate chemistry like pH, dissolved inorganic carbon, and alkalinity. And some of the exciting things here is that these models actually reproduce predictions that have been made by carbon cycle models, such as a big drop in carbonate saturation state following the mid-Mesozoic revolution, and some of these patterns in DIC and alkalinity space during Mesozoic time. So hopefully I'll have more of this data out to the community soon, but I think the general takeaway from here is that, at least at an initial glance, Phanerozoic ooid sizes actually do appear to be reflecting some shifts in seawater carbonate chemistry that have been predicted from other completely independent approaches. Okay, now in my final minutes, I will finally get to these Neoproterozoic giant ooids. So this is this picture I've showed you a few times of the Tonian Spring dolomite. And this is one of these giant ooid units that's in this yellow bar of this histogram. And so I wanted to note that all of these Neoproterozoic occurrences are quite large. They all include ooids that are 5 millimeters in diameter, and most include some that are larger than 10 millimeters. And those 14, 10 are Tonian or Cryogenian in age. This is actually not even all of them. I think since I made this graph in 2020, I know of a few more and I haven't updated it. But anyways, there's at least 10 cases that are Tonian and Cryogenian, and all of those stratigraphically underlie snowball earth glacial strata. Some of them are relatively closely stratigraphically underlie, some of them are separated by more stratigraphy, and we don't have really good chronological constraints on how much time is between them. But regardless, I think it's interesting to think about what we can learn from using this ooid size approach to constrain the climate and chemistry necessary to form these giant ooids, to tell us about the environmental conditions leading into these glaciations. An interesting observation here is that these Neoproterozoic giant ooids aren't just kind of like regular giant ooids. Many of them are like particularly giant. So I'm showing the line here of like the most common size of those early Triassic giant ooids, and almost all of these Neoproterozoic cases are like much, much larger than those. This image over here gives you a sense. It's probably not actually to scale on your screen because this is probably too small, but this is showing you a visual comparison where these circles are all to scale relative to one another, to like what a typical modern sand size ooid would look like. The Ediacaran-Johnny ooid is one that a lot of folks in the community are familiar with. And then these are all giant ooids. The Triassic cases are closer to this size, and many of the Neoproterozoic ones are much, several times larger. So we can plug the sizes of these Neoproterozoic ooids into this model. I'm going to show you a series of graphs like this. So you're now looking at the predicted omega value on the y-axis, bed shear velocity on the x-axis, which is calculated to be a range at which these grain sizes would be transported near the threshold of suspension. And then the contours here are equilibrium ooid diameters in millimeters. So I'm highlighting the 10 millimeter contour, which is that size that's not in all of these cases, but in many of them, and this 5 millimeter, which is basically a size that's in all of these occurrences. And so for this aragonite at 25C case, you can see that some of these size ranges fall above this kind of key omega equals 20 threshold. So although you can kind of capture the like 5 millimeter size at reasonable omega values, there are plenty of documented Neoproterozoic giant ooids that are larger than 10 millimeters in diameter. And it's pretty difficult to explain those under these conditions. And the problem is actually only worse if you assume that perhaps those ooids were originally calcitic rather than aragonitic, because the precipitation kinetics of calcite are slower as a function of a given carbonate saturation state. So this is when years ago, I first ran this model for giant ooids, and I was like, okay, well, I think my model just doesn't, maybe giant ooids are too different from modern sand-sized ooids, and the model just can't explain them because it seems to require implausibly high supersaturation to explain these sizes. But an inspiration from Xiaoyi's work on the early Triassic ooids suggested that maybe this particular assumption about temperature is not correct. And so if instead we use a warmer temperature and an aragonitic composition, because both K and N, these kinetic parameters, are higher at 40 or 37C than at 25, you can see that now we can explain a whole wider range of really large ooid sizes without requiring implausibly high carbonate supersaturation. And a final kind of much more out there idea, because of the stratigraphic occurrence of these ooids underneath glacial strata, is that there's this other really weird but super interesting calcium carbonate mineral. It's a hexahydrated calcium carbonate mineral called ichhyite that tends to only form at relatively alkaline conditions and at near zero temperatures. Also could explain the formation of pretty big ooids at really very moderate degrees of supersaturation. That's in part because ichhyite is less dense than aragonite and calcite, and also because under the right conditions, it can precipitate pretty quickly. And these are pretty interesting, right? These are obviously two very different, effectively end member cases, but at least from a theoretical perspective, either hot or cold seawater could be plausible given the depositional ages and context of these giant ooids. So this is a really interesting to me and potentially helps explain why ooids this large are so limited in terms of their occurrence in the geological record, which is that they require not only unusual seawater carbonate chemistry, but also that coincide with relatively extreme climate. And so these kind of some ideas that I'm going to show you about how one could use these constraints on omega to further constrain seawater chemistry, just using some end member values of calcium to alkalinity and magnesium calcium ratio of seawater. So these are contour plots showing you the different omega values for that 5 millimeter diameter ooid in the dashed line and the 10 millimeter one in the solid line. So you can see, like, under this condition, aragonite at 25C, this would require relatively high pH, high alkalinity conditions to form. We can run these models. These are all free QC models at different end member values of these ratios. You can see, for example, under these conditions, you could explain giant ooids at more moderate alkalinities if the calcium alkalinity and magnesium calcium ratio are higher. And we can look at these conditions over a whole range. In this case, it's hard to pin down exactly what the chemistry is because I'm not using another, we need to know one other parameter of the carbonate system and make a firmer guess about the seawater major ion chemistry to actually do this a little bit more definitively. But in this case, these end member conditions of calcium alkalinity ratio and magnesium calcium are probably closest to correct based on some existing proxies. And these two extreme temperature conditions were the ones that made the most sense in terms of requiring only more moderate degrees of supersaturation. And so these are kind of interesting results because in the warmer case, this seems to require generally lower alkalinity, higher PCO2, which could be consistent with these giant ooids reflecting persistence of a post-snowball greenhouse, particularly in the case of the cryogenian giant ooids. And this case is kind of interesting. In the cold water case, would require higher alkalinity and lower PCO2, which could be consistent with pre-glacial cooling. The one interesting side note about these is that none of these conditions really allow for low pHs of near 7 that have been predicted by some other carbon cycle models for this time. And so I know I'm running short on time, but I wanted to take a second to kind of lay out some evidence because these are two I mean, in my mind, these are just hypotheses that need to be tested, but to lay out some thoughts about which extreme is more plausible. So for this hot case, some pros in my mind are that it does seem to be consistent both in terms of the chemistry, the seawater chemistry it would imply with post-snowball greenhouse conditions. The warm climate state, the warm climate solution already seems like a really good explanation for why there are these early Triassic giant ooids. So it's nice to see that that case seems to occur at least one other time in Earth history. And it is consistent with some interpretations that the primary mineralogy of some of these grains was aragonite. And a major con of this case is it doesn't really seem consistent with some other evidence, and I'm thinking specifically of the McLennan et al. 2020 paper that came out recently, that the late Tonian climate may have been cool before the snowball earth glaciation even started. So it doesn't, I'm not sure it's a conflicting explanation for the Tonian giant ooids. With respect to the cold case, it is consistent potentially with that other evidence of cool late Tonian climate. A lot of the recent work on ichthyoid in lakes has suggested that it's likely really under-recognized in the rock record because it alters diagenetically very, very early. And it could explain why Neoproterozoic ooids seem so much larger than, or well, they are so much larger than early Triassic. They're not just business as usual. But finally, the big issue, I think, in my mind with this is that this is truly just a theoretical prediction. We don't actually have evidence that ooids can form as this other carbonate polymorph yet. But there is a really good way to test this. And this is why I was really excited to highlight this to this group, because I think testing this idea will require a community effort to do a lot more microscopy and collecting of these giant ooids. And I'm highlighting here this figure from Eva Schaller's recent geology paper documenting this characteristic microfabric of the inversion of ichthyoid to vaterite and then calcite during diagenesis. And it has this really characteristic structure that she named goodality calcite, in part because there's 6 waters that get lost as it changes to calcite. And so this is actually much better as a fingerprint of this weird cold water carbonate mineral than the really large, using the morphology of the large euhedral crystals that has been applied in the past. And I think arguably it could, if found, it would be more definitive evidence than isotope thermometry for this time at which it's always difficult to diagnose the effects of diagenesis. So to conclude, what can these giant ooids tell us about pre-snowball marine environments? Well, consistent with the kind of canonical theory before my work, it's clear that a high carbonate supersaturation state is necessary. High seawater magnesium calcium ratio also helps a lot in terms of making either aragonite or ichthyoid be the predominant carbonate phase that would form. Climate and mineralogy are also really important because they modulate the relationship between omega and the precipitation rate. I didn't show this data in detail, but transport frequency is important. So basically this is a version of the models I showed you. And if we let the grains be transported 10% of the time instead of 1% of the time, it's no longer possible to form giant ooids because they, like larger grains, just abrade so much more rapidly because they're so much more massive. And I think what's next is that this is something that my group is working on too, but I'd argue that this tool has a lot of potential to really give us a really detailed and different type of information into these pre-glacial environments, but we really need more and better characterization of the microfabrics and geochemistry of these giant ooids and the surrounding strata to help determine whether they reflect which of these two end member cases they reflect. So none of these are actually giant ooid pictures. So this is a bunch of panels of folks I've been working with recently. You can see a lot of our work in modern environments here, but thanks for your time today, everyone. Sorry I went a little bit long, but I'm happy to hang around and answer questions for a little bit.
Thanks, Liz. You have already a number of people asking questions in the chat, so maybe we can start with I think Paul was first to ask question. Paul, do you want to go ahead or should I read your question? You can unmute yourself and ask. Okay, maybe I read it. So Paul asked, does the reverse size gradient shown on your title slide have genetic significance for giant ooids?
Yeah, that's a really good question. I actually, let me go back and find too many animations. We definitely see reverse grading in a number of these different cases. And I'm not totally sure. I think in the case of some of the giant ooid units that I've spent the most time looking at, in particular, I'm thinking about the rainstorm ones that I worked on back as an undergrad. It kind of seemed to me like the setting that was being captured in the rocks was not necessarily the like actual shoal environment in which they were forming, but rather that they, we're looking at somewhere a little bit off axis that the grains had been transported in some sort of like, grain avalanche or something. And that's because there's not, and this is the same case actually, I think this is Saratoga Spring. There's not a ton of evidence of like dunes in this particular field site, which kind of doesn't, I'm not actually sure that the site is like the like giant ooid factory. And part of that is also something else you might be able to see in this picture is that there's layers of less spherical grains in between some of these layers of really nice spherical giant ooids. And a lot of those are broken pieces of ooids, suggesting that they have experienced like some pretty aggressive transport in order to break them. I don't have a good explanation of that yet, but that's one of the things that I would really like both to do myself and to see done is to see much more detailed characterization of the different types of bed forms in the different giant ooid bearing units.
Thanks. I think a backspring formation maybe has also reverse gradient.
Yeah.
So next question, Itai asked, Itai, do you want to ask your question or should I read it?
Sure, yeah, I can ask. Thanks for this great talk, Lizzy. It's really, really cool stuff. So what I wanted to know, I had two questions. First, are single abrasion events ever enough to remove a whole lamina from an ooid, or do they just essentially polish the surface? And if they are enough to remove a whole lamina or more, does the model then predict that there should be discontinuous laminae? And if so, are such discontinuities observed in natural ooids?
Yeah, that's a good question. So I think at least in the context of what I've observed in experiments and kind of intuition that I've borrowed from the many really excellent geomorphologists who think about abrasion of different types of non-carbonate sedimentary grains. Most of these, these abrasion events are like kind of point collisions. So most of them are going to just kind of like spray off, at least imagining like modern ooids are basically these like balls of somewhat packed in aragonite needles. So it may just be that like, just at the point of collision is where most of the loss of material is centered. In terms of discontinuous laminae, I think yes, discontinuous laminae should exist. And one of the ways in which I've thought about that is in the 2020 JGR paper about Great Salt Lake ooids is that the process of abrasion actually has a sensitivity to grain size. So like if a grain is traveling, is saltating, it should actually preferentially abrade along the most angular bits, or if it's elongated, it should preferentially abrade at the ends of the longer axis. So it'll tend to, like abrasion should tend to reduce the aspect ratio. And so we do actually see some evidence of that in Great Salt Lake ooids. It helps that many of them start out like pretty elongated because they form on these like pill-shaped brine shrimp fecal pellets that you can, if you look at the evolving shape of the ooid as recorded by the different boundaries between the layers, they do get more, they have lower aspect ratio over time than you would predict just by like surface normal growth alone. So while sometimes it's hard to catch like an exact discontinuity sometimes, like you can, in the evolution of shape, you can get a sense that the shape is being modified by abrasion, which might mean that the thickness of individual laminae are not like, you know, they're not equal all the way around the grain.
All right, cool, thanks. And then the other question that I had was, what does the model predict for the size distribution of ooids that are made of a denser material that's harder to suspend, like iron minerals, which are quite common in the Precambrian, but also in certain parts of the Phanerozoic? Or alternatively, if not the size distribution, then the formation environment, right? Because what you need is a certain energy of currents to suspend the materials.
Yeah, that's a really good question. And I've definitely been like variably tempted to like try to apply this model to the kinds of ooids that are in granular iron formation. And I haven't done that because I feel like at least I don't have as good of an understanding of what the precipitation kinetics would be like to actually define an equilibrium size. But at least from the physical perspective, it would basically be the opposite, probably predict it to be the opposite of the ichthyoid case that I explained, that like part of the reason that ichthyoid is an interesting solution for really big ooids is that it's lower density. And so therefore it like for a particular grain size has a lower abrasion rate because it just has less kinetic energy hitting the bed. And so in general, denser minerals would have the opposite relationship, that each impact is going to have more energy. And so abrasion will be higher as a function of grain size than it would be for carbonate, although it's totally also like the strength of the mineral matters a lot too. And so I would actually have to like sit down and plug some like numbers in to try to figure out which one of those would matter more, whether it would be the density or the increased strength of the material that would like win out. It's totally possible to do. And it would be awesome for someone to apply it there.
Gotcha, thank you very much. That's really cool.
Okay, next question from Paul. Paul, do you want to ask or should I?
Yeah, can you hear me?
Yeah.
Mm-hmm.
Yeah, Bob Ginsberg always emphasized that ooids are not pure carbonate. They have a lot of organic matter in them. So I wondered whether there was any relationship between the ooid size and the density. Might large ooids be less dense and therefore be hydrodynamically equivalent?
Yeah, I mean, the density is definitely important. The densities that I use in my model, I actually did the like, took the modern aragonitic ooids I was working with in my experiments and measured their density directly by putting them like measuring their volume displacement for a set amount of mass, and they're pretty close to like, sorry, my Slack is popping up in the background. They're pretty close to what you would predict as the density of aragonite. It's certainly possible that it would make a difference, and I think that kind of gets back to like, I think presumably that's something you might expect to see petrographically or try to characterize better petrographically with like a lot more systematic characterization of all the giant ooids from these different localities. It's a little bit hard because it would be nice to actually like directly measure if there's a relationship between density and size. We just have such a small dynamic range of ooid size in modern environments when we can do that. I have actually seen some ooids that were pushing almost 2 millimeters in diameter in a secret spot along the shore of Great Salt Lake. And so it might be possible there because there's actually probably a range of ooid size in Great Salt Lake between 250 microns to almost 2 millimeters. So that might be a place to try that. That's an interesting idea.
Well, if there isn't a range in grain size, then that's telling you they're not growing.
What?
If there isn't a range of grain sizes in the modern, then they're not growing.
Yeah.
I mean, if they're growing today, there has to be, there have to be baby ones and adult ones.
Yeah. Well,
Why don't you just see whether there's any relationship between size and density?
Yeah. Well, yeah, I think that's a good idea. I'll probably try to encourage one of my students to play around with that with our Great Salt Lake ones where we see the biggest range.
I mean, the Bahamian ooids that Ginsberg showed us thin sections of, there were gobs of organic matter in it. Now, I don't know whether that's secondary porosity, but
wouldn't that just shift the zone of formation, to shallower or to deeper water? Because what you need is essentially the energy to move the grains around. So at a lower density, you could get formation deeper in the water. No.
Yeah, but if there was something that changed over time that affected the mineral organic matter ratio, then perhaps that might be a lead as to why Neoproterozoic ones seem to be larger.
I think it would need to be like a lot of organic matter to make enough of a difference to overcome the like basically the abrasion rate scales so strongly with grain size that unless the grain is has a density that's actually effectively organic matter and not mineralized at all, its abrasion rate is still going to be so rapid for a marble sized grain that you still need a higher precipitation rate to balance that out.
My other question was whether there's any relationship between giant ooids and sea level falls, because when sea level falls, carbonate saturation goes up because of loss of shelf area. And if they were ichite, sea level falls would also be associated with increased phosphorus input from shelf erosion. And phosphorus is well known to favor ichite formation.
Yeah, I'm still I'd say I don't feel like I have a good enough understanding of the relative occurrence of the Tonian and Cryogenian cases relative to sea level curves to pin that down. But it's definitely,
you can do that in the field. Never mind the sea level curves. Just go to the field and measure sections.
Yeah, well, I think that's something we're going to try to do with the Phanerozoic curve for sure. Is compare it to
forget New Jersey and that crap.
Okay. Hello. So next question was Yupei would like to ask your observed ooids, are they associated with microbial mats or stromatolites in the field?
Yeah, I mean, some of these ooids are associated with stromatolites and some of them are not.
Thanks. Why I want to ask question is I want to more specifically ask, maybe the extra polymeric substances or the organic matter are involved in the formation of the ooids. I mean, of course, like the seawater chemistry maybe influence the precipitation of the ooids is a one way. Maybe there's some way also involve the organic matter or the EPS. Just want to ask your opinion.
Yeah, that's a great question. I think the question after yours was a similar one too, that when I was kind of conceptualizing the equilibrium size model in the first place, I intended to be generally agnostic as to whether microbes might be playing some role in ooid formation or not. And the way it's written now is parameterized in terms of strictly abiotic precipitation because we actually have rate laws to constrain that. And I think it's obviously possible that, in my mind, the role of microbes would effectively be able to like accelerate precipitation rate a little bit beyond what you might otherwise predict from a background carbonate saturation state. I think the problem I have, or one of the problems that would have to be considered with respect to giant ooids and microbes being responsible for the entirety of the difference in precipitation rate relative to the like kind of more normal sand size ones is that again, these really large grains we're going to abrade incredibly rapidly, and so anytime they're in motion, they're almost certainly not going to be able to like sustain a biofilm on the surface. Like their abrasion rate is like orders of magnitude beyond those of the sand size grains. So I think it's it would be super interesting to be able to explore a microbial mediated case more quantitatively, but I think what's required is like an actual like quantitative prediction for how specifically a particular type of biofilm, like either, cyanobacteria or sulfate reduction or, whatever community producing EPS would change precipitation rate relative to like the kind of background from those grains forming in a generally carbonate supersaturated environment.
My understanding is that ooids don't form by precipitation. They form by physical accretion. And that's indicated by the aragonite needles, which are oriented tangentially. So I don't think ooids grow by precipitation. That's not my understanding, at least marine ones. They accrete aragonite mud.
Well, the problem with that idea in my mind is that in the type of environment where you can actually move sand-sized grains, all of the aragonite mud is in the wash load. And so I don't know how you would keep enough of it around in the environment for it to stick. And certainly at least in my lab experiments, which I acknowledge are like not the same as the environment, the ooids grew through precipitation and not through the like kind of snowball accretion of mud. Even though mud was produced, but the mud was all like in the wash load in the water column and not not accumulating in the cortices of the ooid.
Okay.
Well, why would the needles go tangentially?
Well, maybe because they're abrading, and that's like kind of tends to favor orienting the needles tangential to the surface.
Would like also continue to ask, in some ooids, there are also some radial lamina. I mean, if they are formed rotated, and how can we explain them in the model? Because, for example, in the Great Salt Lake ooids, the radial lamina are quite abundant.
Yeah, so an interesting thing about the radial laminations in Great Salt Lake ooids is that a lot of those crystals, when you start looking closely at them, actually crosscut the tangential zones in the ooids. And so at least some, and this is not, I'm not the first person to say this, like some of the papers on those from the 70s pointed this out, that there's clearly at least enhancement of the radial fabric in Great Salt Lake ooids that's happening like after the laminate originally precipitated with a less radial fabric. But that said, I mean, the precipitation rate of crystals is related to the carbonate saturation state of the environment. And so in theory, the kind of like traditional idea that radial fabric reflects ooids forming in quieter water conditions where radial crystals might have more time to form on the surface before they roll around and get abraded off a little bit is not, that is totally consistent with the same like kind of size framework. It basically just exists at a lower intermittency value than in marine environments. But I think that personally, I think that the use of Great Salt Lake as this like case of radial ooid formation reflecting lower energy conditions is a little bit more complex because there's clearly some early diagenetic like changes in their crystal fabric. And my student has a paper in review about it right now, so.
Yeah, thanks. Thanks for your reply. I just want to add one more. It's like actually our group also find in the modern creatimati there's a microbial mat, and in the microbial mat and also a recent paper published, we found the ooids exactly formed in the EPS. So I think the ooids formation maybe have different ways. Definitely. Like abatic ones maybe play a role, but maybe there are some ooids are formed by the influenced by the microbial mat or the degraded organic matter.
Yeah, I totally agree. I think that there's likely in reality like a range of ooid formation conditions in which some are like more strictly physicochemical and some may be more microbially mediated. And I think that's why like going back to the like rock record and doing a lot more careful petrography and like comparison with like the surrounding facies is really important to try to like tease apart those like you kind of where on that spectrum you might fall.
Thanks a lot.
Okay, great. So it looks like you, Liz, addressed next comment from Wei Min Ding, unless I missed something. And when was more comment from Dan Mill that you cannot go much higher than 40 degrees and 54 before you sort of animals would not be able to exist. So when Cedric Hagen, Cedric, do you want to ask your question or should I read?
Yeah, sure, I can ask it. Great talk, Lizzy. It was really interesting. I just had a really quick question, and I was just wondering if you knew what age those giant ooids in the Cambrian are, and whether or not they abide by like the predicted transition from the aragonite to calcitic seas. It's about 525 from Porter.
You know, I would need to look more closely at the data table. I think so the data here are colored by the interpreted primary mineralogy. So let's see, I believe the pink ones, no, the black ones are aragonetic, the pink ones are bimineralic, and the purple ones are calcitic. So it's kind of a mixture of everything in that like between like probably 525 and 500. But I have all this data. It's not Artie's, this part of the publication is not out yet, but it's in revision right now. But there's a data table, and I mean, I'd be happy to share it with you if you're interested in checking it out offline.
Okay, yeah, sounds great. Thanks.
Yeah.
Okay, I think Paul already asked his questions, right? So I just about phosphorite.
I yield the floor to Eva Stuecken.
Yeah, so, but Eva, are you still here?
I think she wrote her question in the chat.
Yeah, I did. Yeah, but I can also ask it. So I was wondering, so you may have mentioned this, but so I was wondering, when you say giant ooid, does it mean that you have more laminae, or does it mean that the number of laminae is the same, but the laminae is thicker compared to small ooids? And I wondered if that would tell you something about the hydrodynamic regime and also the chemistry in which they form.
Yeah, that's a really good question. I didn't include any good petrographic images in this slide set, but yeah, in general, they're most of these giant ooids are basically like a small nucleus. Like it's not just like a bigger nucleus with this, you know, kind of a thinner cortex, and they have many laminations. It's hard to count exactly how many because they're old enough that the laminae themselves are much less well preserved than, for example, in the like modern ones I have from the Turks and Caicos. But yeah, in general, there's these ooids are all a small nucleus, a thick cortex that's composed of many thin laminae, not more thicker laminae. But I think it's hard to explicitly compare the lamina thickness with, at least with modern cases, just because like the diagenesis has made it impossible to like distinguish individual lamina thickness in the same way that we can see in like modern ooids.
Okay, I guess, yeah, so my related question would have been if that basically means that these ancient ooids are just sort of kept alive longer, that they're active for longer than modern ones for whatever reason, but if you can't really distinguish between laminae, then it probably is difficult to answer.
Yeah, I mean, I think it's not unreasonable to suspect that like the lifetimes of these ooids might be longer than the modern ooids. And I know, for example, like in that probably the lifetime of ooids, it depends on other things in their environment. You know, it's going to depend on like whether the kind of net depositional rate is fast enough that like when, you know, when they're trapped in a bed form, that bed form just like never moves again and gets buried. But like, for example, the lifetimes of ooids in the Great Salt Lake, where the transport intermittency is much, so they're moving much less frequently than in a modern marine environment, and the kind of net depositional rate, like the net rate of formation of new sediments, is pretty slow. Those ooids have been shown to be forming over like the past like 6,000 plus years, as compared to like 1,000 years in some of the modern marine settings like the Bahamas and the Caicos. So there's definitely, at least there's a relationship between like how often they're moving and like yeah, like kind of the rate of creation and deposition and sediment burial in those environments.
Okay,
so it's
thanks.
Yeah, hard to say specifically.
Okay, next question from Kate Giles. Do you want to read it or should I read it?
I can just ask you. That was really interesting, Lizzy. I'm really fascinated by these, the giant ooids, but I'm real familiar with these piezoid facies in the Guadalupes, in the Permian Reef complex. I don't know if you've looked at those, and maybe those would be considered giant ooids, though I think they're not. I'm just wondering how do they compare? How do you separate them? Because to me, both in thin section and in outcrop, they look so similar.
Yeah, I feel bad that I should have included a couple more petrographic images in here, but it's, you know, it's hard to take good petrographic images of giant ooids because they end up being large, because you have to do a mosaic of like many, they're so big that they're so much bigger than like the field of view. But in general, like, I think what sets apart these, what I've called true giant ooids in this talk, like some of the early Triassic ones and basically all of these Neoproterozoic ones, is that with respect to their fabric, they are very much like just really overgrown modern marine sand-sized ooids, which means that they have a very small nucleus. It's often pretty hard to tell what exactly it is, because it was probably just, you know, some peloid or some fragment of something. They're often not well preserved, and because of the kind of thin section cut effect, the nucleus is so small that often when you make a thin section, like it doesn't pass through the center of mass of the grain. So many of thin section views of these don't even include the nucleus, but they have this like very finely and evenly laminated cortex, and the grains themselves are, when they're haven't been compacted too much, you can tell that many of them are incredibly spherical, and that in many cases their shapes evolve towards a more spherical shape, like kind of outwardly, like even if they were more had a higher aspect ratio initially, they get more spherical over time, which is a really good fingerprint that those grains have been subjected to abrasion and have rolled around. Like abrasion is the best process to make a non-spherical grain more spherical much more quickly than surface normal growth. So I think that those are some of the things that distinguish these giant ooids from other types of coated grains that like other types of piezoids, which I think can that term can cover a lot of different types of grains, is like the nature and geometry of the laminations and the actual shape and shape evolution of the grains themselves, and the very small nucleus that suggests this like process similarity with like a regular sand-sized ooid.
Yeah, the piezoids in the guads, there's a lot of what you would call composite, like their nucleus is composite grains pulled together and then those get coated on top. I think the giant ooids, you don't ever see that composite nature, right?
Yeah.
Yeah, and there's depositional bed forms here, unlike Vados piezoite. So you wouldn't get that in Vados piezoite unless it's reworked. If Dunham's correct about the Permian Basin.
Yeah, a lot of people debate the Vados nature as being more an overprint.
Okay, next question was from Susanna Porter, and she might have left already. So I will read her question. Great talk, Lizzy. I was wondering what you thought of Strauss and Tosca's 2020 model suggesting very high supersaturation in the Tonian due to the inhibitors like phosphate, and whether that could explain this large ooids. And she might have left by now. But...
yeah, this is a really great question. And I think that those two papers are really cool, and there are a lot of there've been a lot of food for thought for me. I think it would be really interesting to, and totally possible to, try to incorporate those effects into the way that something like the ooid size model parameterizes precipitation rate. I think I'm not sure if I'm remembering correctly. I think the really important thing to know about the effect of these inhibitors is whether it moves the threshold of homogeneous nucleation, but the overall carbonate precipitation rate relationship as a function of supersaturation stays the same, or whether inhibitors also fundamentally shift the precipitation parameters. But I think that's certainly another possible way around these ooids requiring these, they have to require these extremely rapid precipitation rates. So potentially if the kinetic parameters of carbonate precipitation remain the same, that it can precipitate quickly but just not crash out of solution, then that would be a good explanation. And that's certainly something that I'm looking towards thinking about applying in future iterations of this model, given better constraints on concentrations of those inhibitors and how specifically they affect those kinetic rate laws.
Okay, great. And I think Eva already asked your question, and was a comment from Tessa, but I'm not sure exactly about oncoids. But so I think
that was a comment back to the piezoid question, which again, oncoids are different in terms of the nature of the laminations, that they are not smooth and even, but they are crinkly, and so their formation mechanism is different. And I recently have been kind of vaguely thinking about thinking about something kind of analogous to the equilibrium ooid size model for oncoids, but I think it would be really different. There are some pretty cool proto-oncoids in Great Salt Lake that would be fun to do flume experiments with and watch what happens to them as they roll around, but I haven't really explored that too much. I think it's a pretty different case when you have you know, a like robust microbial mat on the surface. Those certainly are much less dense than they would be if they were all mineral too.
Great. So looks like we caught up on chat. So if anyone has any comments or questions, feel free to unmute yourself and ask.
Hey, Lizzy, this is Carol Daler.
Hey.
Hey, I really enjoyed your talk. Thanks so much. And I did have that same question about oncoids and if they could be some kind of, could there be a continuum between ooids and oncoids, and are they kind of at the end of a spectrum? But it sounds like, well, you've answered that question. Do you think there's tweeners?
Oh my gosh. I mean, yeah, I think it really gets to this, like, what we were talking about earlier with, like, in my mind, I think the most likely case with respect to like the role of microbes in like ooids, including just like regular ooids, is that there's a spectrum from some cases that are really not microbially mediated. And that's one of the things I argued in my 2018 paper from the ambergris shoal that I didn't really have time to talk about here, and that in other cases they may be more microbially mediated. So for example, a project that one of my students is now out for review found that there might be a microbially mediated mechanism for a bunch of magnesium silicate minerals that are within the cortices of Great Salt Lake ooids, because those minerals basically shouldn't be there based on the relatively low pH of the lake water, and they happen to coincide with elemental sulfur that probably is only there because of microbial sulfur cycling. So I think even in my own work, in my own experience, I've seen cases that are like appear to be at different places on a spectrum with respect to the role of microbes in just regular sand-sized ooids. I think one of the aspects of oncoids that would be important goes back to Paul's original or first question about density, because at least these kind of oncoid-like grains that I've played around with in Great Salt Lake are have very low density, because they really are more like moving kind of crunchy microbial mats than actual mineral grains, at least right now. And so the nature of the relationship between their movement and abrasion is going to be really different. And I'm also not sure in my model framework, abrasion, the actual amount of material that's abraded depends on a number of things, but some of those are the material strength of the mineral. And I'm not even sure how you would go about characterizing the Young's modulus of the sticky microbial mat layer on the surface of some of these oncoid-like grains in Great Salt Lake. And so, I mean, it would be totally interesting to try to characterize that, but I think there are some enough kind of mechanical differences between if you actually have something that's mostly micro versus mostly mineral, how that growth versus abrasion process would work out.
Yeah.
Yeah.
Well, thanks. I actually have a comment as well. And the 2R group in Grand Canyon has piezoids in the upper member, the Walcott member, and I've called them piezoids for years, and the previous workers called them piezoids, but they're giant ooids. I mean, after seeing your talk today, those are giant ooids.
Yeah, I think is that the layer that my colleague Carl Simpson went on the Grand Canyon trip a couple years ago? So I have 2 of those.
Awesome. He came last year, and many of them are silicified, but there are, if you look hard enough, there are some that are not, and they range in size, and there's also ooids. And I see that you're on the participant list for that April trip. And all I can do is highly encourage you to come on that so that you could sample those and add some more giant ooids to your database.
Yeah, absolutely. That would be awesome. I think like I said, that was one of the examples in my mind when I said when I was showing the histogram that that's not even a completely exhaustive list of all the ones that are potentially out there. So yeah, I'm really looking forward to that.
Are you coming?
Yeah.
Oh, that's very good news. That's great.
Yeah.
Okay, well, thanks. And your talk was wonderful.
Thank you.
Okay, thanks. Any other comments, questions?
I think the phosphorus inhibition idea is an interesting one because these phosphatic skeletons can only mean that phosphorus is not a limiting nutrient in the Tonian.
Yeah. I think, like I said, I think the only thing holding me back from really like plugging that into the model is just a better understanding of how not just the inhibition shifts like thresholds of nucleation, but actually how it might shift rate laws. And I would have to look back at those papers to remind. I feel like I didn't see that relationship there, but maybe I was missing that, or maybe that's what they're working on next.
Well, I think organic matter is important for carbonate production also. I mean, there's lots of indications that just dead organic matter helps to overcome nucleation inhibition or accelerates carbonate growth or something. There's definitely a connection.
Mm-hmm.
There is a comment or question from Sarah.
Do you have a petrographic mic at Caltech?
Yeah, I'm at CU now.
I never
but
had one at Harvard, I admit. So,
yes.
did you collect ooids when you were in the Turks and Caicos?
Oh yeah, we have so many slides of ooids from the Turks and Caicos. Yeah. They actually do not have that much organic matter in them. Almost all of the organic matter is associated with the endolithic microborings and not the layers between laminae. Mm-hmm.
So it's aragonite needles, is it?
Yep.
Okay, so there is a question from Sarah Gales. Sarah, do you want to ask or should I read it?
Yeah, I'm happy to. Great talk, Lizzy. I'm super sorry to ask you one more question. I'm just curious, for the rainstorm giant ooids, I mean, that cement and those geopetals in there, it had to be really quick to, they're transported as blocks. So what do you think about that and kind of the environmental and formation story?
Yeah, first of all, I'm really sorry that I never followed up at trying to join you in the field to look at them. I think, was that in the early pandemic days? I don't even know what is time anymore.
No worries.
Yeah, I think, I'd always, when I first worked on the rainstorm giant ooids, for anyone else who may not know the context here, those ones have this, I don't think I have a picture in here that shows it, but many of the ooids have this really interesting geopetal structure that alternating layers of the cortex appear to have dissolved and then the other layers have dropped down. So when I look, they're basically these dropped cortice features. And so it's this weird nesting feature. And when I was first working on those, I kind of thought maybe that suggested that they formed as that they were bimineralic, and there was some reason why one of the primary types of layers was dissolving so easily during effectively earliest diagenesis. It's so one of the important things that happens when ichthyocyte is altering to vaterite and or calcite during diagenesis is that there's this huge volume reduction. And so recently I've been
the organic matter. That's the organic matter.
Well, where is it going?
It's going to the air. It's making oxygen and water.
Yeah, I don't know. I haven't looked at those.
Or alternatively, it's making bicarbonate.
I haven't looked at those since 2010, but I think the the nature of those is telling you something pretty interesting about like that the environment was probably oscillating in some way while they were forming, regardless of what the composition of those missing layers is. There was clearly some environmental reason why some layers were had a composition that was not so quickly dissolved diagenetically, and other ones did not. And I think, I don't know, to be perfectly honest, I haven't looked at them enough recently to like.
Burial and diagenesis. You know, conditions aren't time, you know, can be time variable.
Yeah, well, these are basically like the geopetal features are forming like as the ooids are like cementing. They're just incredibly early. They're super interesting.
Yeah, well, if the water's warm, it doesn't take long for respiration to get rid of the organic matter, especially if it's oxygenated.
Okay, so any more questions? If not, looks like people are starting to thank you, Lizzy. Thanks, it was great talk and great questions from people. So that's what interesting about the seminars, that we can spend time.
Yeah, the time dependence of the occurrence for sure.
Okay, so we'll meet next week at the same time. Talk to you later. Thanks, Lizzy.
Thank
Thank
you.
you, Andre, and thank you, Lizzy.
Thanks.
You guys. Bye, Paul.
All right.